You're most welcome to this second episode of Atomic Structure. The previous time, we looked at the introduction of atomic structure. We looked at the structure of an atom. We looked at isotopes and how we use atomic mass and atomic numbers. Today, we are going to begin with how to write an electronic configuration. How to write an electronic configuration of an element. And like from last time, we had agreed that if you want to look at the structure of an atom, there are two basic parts where we agreed that each atom has a nucleus and it has what we call energy levels. So when we look at an electronic configuration in this area, we want to look at arrangement of electrons on the energy levels around the nucleus of an atom. Around the nucleus of an atom. And if you still recall, we said in any neutral atom, protons are equal to electrons. Therefore, we can write our electronic configuration by use of what we call, we can write our electronic configuration by use of atomic numbers. So electronic configuration can be obtained from atomic number, or simply number of electrons, but not neutrons. So below we are going to suggest different atoms, the first 20 elements, and their atomic numbers. Then from there, we shall proceed and write the possible electronic configurations depending on what we have seen. So if we call here for the first 20 elements in the periodic table, you're going to realize that the simplest is hydrogen with atomic number 1. Second to hydrogen is helium with atomic number 2. Lithium with atomic number 3. Beryllium with atomic number 4. Boron with atomic number 5. Carbon with atomic number 6. From carbon, we meet nitrogen with atomic number 7. We meet oxygen with atomic number 8. We meet fluorine with atomic number 9. Neon with atomic number 10. From there, we go to sodium, atomic number 11. Magnesium, atomic number is 12. Aluminium, atomic number is 13. Silicon, atomic number is 14. Phosphorus, atomic number is 15. Sulfur, atomic number is 16. Chlorine, atomic number is 17. Argon, atomic number is 18. From argon, we go to potassium, atomic number 19, and lastly calcium with atomic number 20. Since we said that atomic number can give us an electronic configuration, if there is only one electron, for example, if I want us to look at electronic configurations, the following should be put into consideration. Number one, first shell or first energy level around the nucleus. First energy level around the nucleus is filled up by only 2 electrons. That is number one. Successive energy levels after the first energy level are filled up by a maximum of 8 electrons. They cannot exceed 8 on one energy level. So when we start trying to come up with the electron configurations of these first 20 elements, such that we can be very clear on what we want to mean, I will try to represent my write-up with drawings to show you the typical arrangement of these electrons, such that we are very, very clear. I'll begin with element number 1, which is hydrogen. Hydrogen has a symbol of capital H, and its atomic number is 1. When you come to draw, we take an example. If this is the nucleus of hydrogen, around the nucleus we shall have one energy level or one shell, and that shell will only have 1 electron on it, because the atomic number shows us that hydrogen has 1 electron. Therefore, the electronic configuration of hydrogen is simply 1, because hydrogen has only 1 electron. Then we go to element number 2, which is helium, symbolized with capital H and a small e, with atomic number 2. From this write-up, it shows that helium, if you draw the nucleus of helium, around the nucleus we shall find an energy level, and this energy level has 2 electrons. And since we said from here that the first energy level is filled up by 2 electrons, it means the energy level of helium is fully filled. So this one has a fully filled energy level. We shall see how to classify such elements. Therefore, its electronic configuration is simply showing us that the first shell has 2 electrons. That's how we shall write for helium. Then from there, we shall proceed to more elements. Allow me to clear this side as I'm maintaining this side here, such that we can get to know element number 3. Element number 3, we are finding it as lithium, which is symbolized with capital L and a small I. The atomic number is 3. Therefore, if this is the nucleus of lithium, the first shell must get 2 electrons. That's the maximum it can take up. If we subtract these 2 from the 3, it means 1 electron is left, and that electron will be placed in the second shell, such that the electronic configuration shows that lithium has 2 electrons on the first shell, and if you jump from the first shell to the second shell, you will only find 1 electron. So the electron configuration will become 2 to 1. We proceed from lithium. We proceed to other elements. Element number 4 is beryllium, symbolized with capital B and a small e. Atomic number is 4. So first shell, this is the nucleus. First shell takes up a maximum of 2 electrons, and the second shell will take the balance, which is 2. So it will also have 2 electrons. Therefore, electron configuration will be 2 electrons on the first shell and 2 electrons on the second shell. Number 5, we are going to find boron, symbolized with capital B. We shall find out that atomic number is 5. Therefore, if this is the nucleus of boron, the first energy level around the nucleus takes up a maximum of 2. So if we remove these 2 from the 5, a balance of 3 electrons will be left, and those 3 electrons are going to be arranged on the energy level, which is the outermost. So we shall find the electron configuration showing us 2 electrons on the first shell and 3 electrons on the second shell. Remember that the second shell, we shall only leave it if the second shell has a maximum of 8. So the coming elements, we shall continue filling up the second shell until we reach an element that has 8 electrons in the outermost shell. So we shall go to element next, which is having atomic number 6, and that is carbon. So our next is element 6, which is carbon, symbolized by capital C. Atomic number is 6. So if you draw the structure of carbon, you will find that the first energy level has 2 electrons, but the second energy level will have 4 electrons, the balance on the 6. So we shall have 1, 2, 3, and 4. Therefore, electron configuration will be 2 to 4, because the outermost shell has 4 electrons. Element number 7 is nitrogen, symbolized by capital N. Atomic number is 7. Therefore, if we draw its structure, first shell has 2 electrons, and second shell will have the balance, because if you subtract 2 from 7, the balance is less than 8. So the 5 electrons will be on the outermost shell of nitrogen, such that electron configuration becomes 2 to 5. Then from nitrogen, we shall meet element number 8, which is oxygen. Oxygen, which is capital O as its symbol. Atomic number is 8. Therefore, if we draw its structure, if that is our nucleus, first energy level filled up by 2 electrons, that is the maximum number. Then second energy level can take up a maximum of 8. But on this 8, we have already placed it 2 on the first energy level. Therefore, the remaining 6 will be put on the last shell. Therefore, electron configuration becomes 2 to 6. As we continue, different elements have been finished in terms of writing their electronic configurations. We shall go to element number 9, which is fluorine, symbolized by capital F with atomic number 9. Therefore, when we draw its structure, first energy level has 2 electrons. On the 9, if you subtract off 2, you remain with 7. So we shall put 7 electrons on the outermost shell, and its electron configuration will become 2 to 7. We move to element number 10. Element number 10 is going to be a neon, symbolized by capital N and a small e. Atomic number is 10. We are going to find out that if this is the nucleus, first shell, 2 electrons, second shell, if we get the 2 and subtract them from 10, the second shell will remain with the maximum number it can hold, which is 8. So you come here and put 8 electrons in pairs. So we shall put 4 pairs, which makes the total number to become 8. Therefore, our electron configuration becomes 2 to 8. Now, the second shell is fully filled. That means in case we have another element coming, that element should have or should attain a third shell, because the second shell can no longer accommodate any more electrons. So when we come to element number 11, which is sodium, symbolized by capital N and a small a, atomic number is 11. If this is our nucleus, first shell will take up a maximum of 2 electrons. Second shell has already accommodated 8, so we shall place them there. So far, those are 10 electrons. But remember, sodium has 11. Therefore, we shall include a third shell where we shall place 1 more electron, such that sodium has 2 electrons on the first shell, 8 electrons on the second shell, and only 1 on the last shell. So the number of shells sodium has differ from the number of shells possessed by nitrogen. it differs from the number of shells possessed by lithium. However much, both have one electron in the outermost shell. Sodium has 3 shells, while lithium has only 2 shells. So we are going to realize when we come to the periodic table that this can create a difference in terms of the group and the period to which an element belongs. We are continuing with element number 12, which we agreed that it is called magnesium. Then we shall go to element number 13, which is aluminium, and see how we can continue with what we are seeing here. Element number 12 is magnesium, symbolized by capital M, and our capital M should have the sharp corners with 12 as the atomic number. If this is the nucleus, first shell possesses 2 electrons, second shell possesses a maximum of 8, it cannot exceed 8, and now those are 10 electrons. That means the last 2 electrons are going to be found in the third shell, which means that our electron configuration becomes 2 to 8 to 2. Come to element number 13, which is aluminium. And this one, I'll request that we simply write the electron configuration, and in your practice, you can go ahead and draw the structures. Aluminium is 13, symbolized by capital A with a small l. Electron configuration will be 2 to 8 to 3. Element number 14. Element number 14 is silicon, symbolized by capital S, small I. Atomic number is 14. Electron configuration is 2 to 8 to 4. Element number 15 is phosphorus, symbolized by capital P. Atomic number 15. Electron configuration becomes 2 to 8 to 5. We move on to element number 16, which we agreed that it is called sulfur. 17 is chlorine, 18 is argon, 19 is potassium, and lastly 20 is going to be calcium. And we shall conclude the process of writing electronic configurations. So element number 16, we agreed it is sulfur, symbolized by capital S. Atomic number is 16. Therefore, electron configuration is 2 to 8 to 6. 17 is chlorine, symbolized by capital C, small l. Atomic number 17, which means electron configuration is 2 to 8 to 7. 18 is argon, symbolized by capital S, small r. Atomic number is 18. Therefore, electron configuration is 2 to 8 to 8. And on argon, we find out that the third energy level is now filled up. That means an element which comes next, that is potassium. Potassium, symbolized by capital K with atomic number 19, it will enter a fourth energy level because the third energy level is filled up and cannot take up any other electron. So we shall find that the electron configuration is 2 to 8, to 8 to 1. And lastly, 20, which is calcium, will be 2 to 8 to 8 to 2. Calcium symbol is capital C small a, atomic number is 20. You must arrange these electrons in such a way that they total up to the atomic number given. If the electrons are fewer than the atomic number given, it means you're not dealing with a neutral atom. You might be dealing with either a cation or an anion, depending on what we are going to see next. Now, where and when do we use electronic configurations? Where do we use electronic configurations? How do we apply the knowledge of electron configurations in the study of chemistry? Application of knowledge of electronic configurations. Electronic configurations. These electronic configurations allow us to understand quite many things, including the following. Number one, electron configurations are going to allow us to know whether an element is a metal or a non-metal. In simple terms, what we are considering here are the number. On this point, consider number of electrons in outermost shell. And what we are going to consider, if the number of electrons in the outermost shell is between 1 to 3, those are going to be called metals. Between 4 to 7, we are going to call them non-metals. And those with fully filled shells, we are going to call them inert. If you don't call them inert, you're going to call them noble. If you don't call them noble, you are going to call them group 8 elements. So these elements do not react because they have no valency. Their outermost shells are filled up. If I try to use this knowledge to identify the elements which are going to be called metals, I think we can come up with those elements using the electronic configurations. Number one, I'll begin with, I'll have lithium, which is 3. It is 2 to 1. I'll go to beryllium, which is 4, and it is 2 to 2. I have, I'll move on to boron, which is 5. Electron configuration was 2 to 3. Then I'll jump from there, go to sodium, which was 11. Electron configuration was 2 to 8 to 1. I'll have magnesium, which was 12. Electron configuration was 2 to 8 to 2. Aluminium, which is 13. Electron configuration is 2 to 8 to 3. I'll go to potassium, 19. 2 to 8 to 8 to 1. and calcium, which is 20, and 2 to 8 to 8 to 2. So all these metals, when you focus on the outermost shell, electrons are between 1 to 3, and these elements will be called metals. Those with the outermost electrons being more than 3, we shall refer to them as non-metals. Number 2, the knowledge of electronic configurations allows us to understand the period to which an element belongs. So point number 2, to identify the period in the periodic table to which an element belongs. For example, this one is going to depend on the number of shells present in an atom. For example, if I write these electron configurations 2 to 3, 2 to 8 to 3, and 2 to 8 to 8 to 2, you're going to find out that because this one has only 2 shells, it belongs to period 2. This one has 3 shells, therefore belongs to period 3. This one has 4 shells, therefore it belongs to period 4. So in the first 20 elements, your task is to find out which elements are belonging to period 2, which elements are belonging to period 1, and which elements are belonging to period 3 and 4. Another point is to identify the group in the periodic table to which an element belongs, depending on the number of electrons, in the outermost shell. For example, if I write the following electron configurations here, I'm going to be identifying the group to which each element is belonging. 2 to 1, 2 to 2, 2 to 3, 2 to 4, 2 to 5, 2 to 6, 2 to 7, 2 to 8. If I come to classify the groups to which each element belongs, 1 electron in the outermost shell, you belong to group 1. 2 electrons in the outermost shell is group 2. 3 electrons, you belong to group 3. 4 electrons in the outermost shell, that is group 4. 5, you belong to group 5. 6, you belong to group 6. Here it will be group 7, and lastly group 8. And groups are written in Roman numerals, while periods are written in numbers. So you will find out that that is also another way of identifying or trying to use the knowledge of electronic configuration to classify different compounds in the periodic table. Another aspect or something else to allow us understand chemistry by relating electron configurations to to the chemistry, we are going to be discussing. Point next is to identify valences of different elements. These valences are going to depend on the groups. If you belong to group 1, that means your valence is 1. Group 2, valence is 2. Group 3, valence is 3. Group 4, valence is 4. However, from group 4 downwards, subtract the outermost electrons from 8. For example, if I'm having oxygen, which is 2 to 6, I'll get 8 minus 6, which gives me 2. So 2 becomes the valence of oxygen. That means if I'm in group 5, my outermost electrons are going to be 5. So I'll get 8 minus 5, the valence will become 3. Group 6, outermost electrons are 6. So you get 8 minus 6, the valence is 2. Group 7, the valence will be 1. And group 8, the valence will be 0. Because of this, members of group 8 do not react. That is the reason as to why we say they are inert, or we call them noble gases. We give them a specific name. So that is to do with the valences of different elements, as valence is going to be the combining power of an element. Next idea, which we can generate from electronic configuration, from the information of the electronic configuration, is to know whether an element forms a positively charged ion or a negatively charged ion. To identify the type of ion formed by an element. Cations, these are positive ions, and they are only formed by metals. So metals are going to be found in group 1, group 2, group 3, and the transition elements. But among the 20 elements, they are not part, so that's why I've not discussed them. Then there are those which we are calling anions, which are going to be the negative ions. Negative ions are formed by non-metals. So we are going to find them in group 4, group 5, group 6, and group 7. So that's how we are going to be using the information of electronic configuration to try and answer as many questions as possible. In our next episode, we are going to see how these ions are formed, and we are also going to look at chemical bonding. Please, I request you to continue subscribing to my channel, like the videos, comment in case of anything, and share my link with other colleagues such that we can boost the performance of chemistry at large. Thank you for watching. Continue to watch more episodes in the series of atomic structure and other topics to draw more courage, and light on chemical concepts. Thank you very much. I remain Smart Science.